Hello and welcome everybody to the course Crystal Engineering Chemistry Beyond the Molecule. So in the last video we introduced halogen bonding, talk about angles, talk about sigma holes, something like this. Now in this video or in this lecture we will have a look how we can use it in crystal engineering to design desired crystal structures. First, talking about energy. Comparable to hydrogen bond, there's a very broad range of energy in intermolecular interaction regarding hydrogen bonding. You know? Well, for example, there's only 5 kilojoule per mole in case of chlorine-chlorine intermolecular interaction, and on the other side 180 kilojoule per mole in the interaction of this anion and iode. So this is in the region of covalent bonds, no? 180 kilojoule. No? And don't forget the Boltzmann energy is 2.5 kilojoule, and something like chlorine is only a little bit higher, like Boltzmann energy. Now, have a look how we can use it. First of all, if you look in the crystal structure database and look to, for example, bromine and iodine substituted compounds, you very often find that's a similarity isostructure. I've shown you some examples on one of the beginning slides of the lecture series. No? For example, if you look at iodobenzene and bromobenzene, here the cell constants, you see 15, 11, 7, 14, 11, 7, there's only a little bit enlarged in the constant A, but makes sense. Iodine is a little bit bigger atom. And it's exactly the same pattern if you look in crystal packing, this isostructure. No? Very often you will find. So, if you see iodine and bromine compound, directly think, okay, if you have a iodine compound, crystal structure, maybe in the case of bromine, this is isostructure similar. Yeah? And this similarity principle can be enlarged. Yes. Have a look on this compound. This is a ferrocene derivate. No? This is huge, it's a big compound. Yes. And here looking to the residue R. This is a chlorobenzoyl substituents with different numbers of chlorine substituents at a residue, no, of this big compound. And very strange, you will see there's a similarity to something like this, not iodine but chlorine. Yeah? For example, 2-chlorobenzoyl ferrocene compound. This is a crystal structure. This is an eye sketch, no? Only from the packing. You see it here, and very similar to chlorobenzene. Yeah? Same situation. Or if you're looking to free substituted chloro substituted benzoyl ferrocenyl compound. Once again, you see with the arrangement, molecular arrangement of the layered structure, pp interaction, and exactly the same in trichlorobenzene. You know? So with similarity principles, you will see very often in the case of halogenated compounds. Another very interesting issue are X-epsilon contacts. X is the halogen, and epsilon, something like nitro group, cyano group, P system, or with acetylene unit. With a weaker intermolecular interaction, and in the case of the weaker halogen bonding, it is very, be careful. The geometry is very interesting. The pattern of the X and epsilon substituents. I will show you. So first of all, have a look on iodine nitrosinton. This is a very robust synton and is really very useful in crystal engineering. It has about 20 kilojoule per mole energy, and you can think about high symmetrically unit, asymmetrically unit, or only one point interaction of one iodine and oxygen, something like this. All of these types exist. And look, for example, the crystal structure database and look to this 1,4 pattern. You will find this very nicely changed. Iodine interaction high symmetrically to the nitro group of a neighboring molecule, and so on, and so on, and so on. Very nicely changed. And you can use it not only in this case. For example, this case here, we have 3 aromatic backbones, 2 iodine, and this is dinitrobenzene. And once again, you will see this very nice change. Okay? Good. This is nice. It seems it's very useful. Okay. Let's try. Have a look on this compound. Iodine, nitro, nearly similar. 1,4 position, 1,3 position. Think about the crystal structure. What do you suggest? Which crystal packing motif would you expect? Wait a minute. Think about it. Well, one suggestion could be something like this here. Okay, in this case we have a chain. Yes, chain structure. So looking to this position, 1,3 position, one suggestion could be something like a ring structure, 4-membered, 5-membered, 6-membered, I don't know. But ring system. No. If you look to the crystal structure, you will see there's no ring structure, first point. And there's no iodine nitro interaction. This is the crystal packing of 3-iodo-nitrobenzene. You see interaction of a nitro group, neighboring nitro group. You see interaction of iodine atoms. Nice example to illustrate, and that is the case of X epsilon contacts here, of halogen bonding. The substitution pattern is extremely important, yes, in crystal engineering. Only 1,4 position, in the case of iodine and nitro group, only 1,4 positions form this nice linear chains. And exactly in the case of a 1,2 position, you will not find a change. You will not find something like this. And the second thing, very strange, talking about similarity, there is a similarity. In the past, we have shown similarity between chlorine and bromine atoms, and there is a similarity between nitro and cyano. If you look to the crystal packing of 3-iodo-benzonitrile, you see, this is 3-iodo-nitrobenzene, and this is 3-iodo-benzonitrile. You see, exactly the same. You can really see there's a similarity switching from nitro to cyano groups. You will see very often If we look to the halogen bonding, X epsilon halogen bonding, very often there's a similarity. You can really change nitro group by cyano group. This has no impact on the molecular aggregation. Okay. Now, going on. Next step. X epsilon context in life science. Is it useful? And directly the answer is yes. What we see in life science very often is an interaction of C carbon halogen bond, this unit, with a P system. And very often in such a way that this CX stick is directly orientated on the middle of a P system. Very often you will see it in the protein-ligand interaction. Yes, this is on the top a neighboring aromatic system. Here you see, this was a figure, this is here the aromatic system, anything, and a residue with the chlorine subsequent. So it's not only restricted to bromine and iodine, also chlorine. This is orientated on the middle of a P system. Very often you see the angle around about 90 degrees. It was very nice, this is a very interesting contribution here in Angewandte Chemie 2009, and very often shown this unit is seen very often in life science and such protein ligand interactions. Another very nice example is this holiday junction, published in Science. This is the holiday junction, and have a look here. This is the interesting unit. First of all, holiday junction, 4-stranded DNA junction, and the key structure intermediate during homologous recombination of DNA. This is the importance of holiday junction. And what we see is we can stabilize this function by using halogen bonding. Yes, and this junction can be stabilized by bromine, this is with magenta here signed atom, bromine, oxygen intermolecular interaction. This is here what I have done is, by substitute thymine by bromo uracil. And this leads here to a strong intermolecular interaction, the stabilization of a holiday junction. Yeah? Okay, let's compare halogen bonding with hydrogen bonding. We have seen we can use sigma hole in crystal engineering in such a way that we can use it in directionality. And we can tune the sigma hole by switching, for example, from one halogen, from chlorine to bromine to iodine. This is possible. Iodine will lead to a higher sigma hole. Both of them, halogen bonding and hydrogen bonding, are directional, but only halogen bond is tunable. This is very important. Hydrogen bond is not really tunable. And in crystal engineering, the usage, mostly what you see is such a way that you have a competition, that you substitute halogen bonding by hydrogen bond, or hydrogen bond by halogen bond. So it's a competition to substitute one interaction by the other. On the other side, this could be useful in such a way there's a cooperation of both, that you can use hydrogen bond together with halogen bonding to design desired crystals. I will show you some examples in one of the next videos. videos talking about the usage and applications. So as an appetizer, thinking about hydrogen bonds and halogen bonding with usage, have a look on the molecular interaction of imidazole derivatives. Very nicely contribution, 2013 crystal drawing design. And the author analyzed the crystal packing of some different imidazole derivatives. This is imidazole. This is a methyl substituted imidazole. This is a methyl plus 2 bromine substituted imidazole. And here's a bromine and 2 cyano groups. And additionally, this is a hydrated form. Question is now, which crystal packing you suggest? No? So I would say stop this video at this point and think about it. Think about which interaction would you predict for the different compounds. Okay? And then we continue. So, hello, coming back. Well, first of all, think about possible interaction. Huh? In the case of imidazole, we would suggest NHN interaction of the neighboring here and PP intermolecular interactions. In the case of a methyl substituted compound, similar, and maybe interaction of a methyl group with a nitrogen, or the interaction of a methyl group with a P system. In the case of a bromine substituted, so we know this form, and additionally interaction, halogen bonding, bromine-bromine interaction or bromine-nitrogen interaction. And in the last compound, all of them, and additionally bromine cyano and cyano HN, or anything with water. You know, water, and water, I don't know, everything. So, with a suitable interaction. Now have a look in the crystal packing. In the crystal packing of the imidazole by itself, we see exactly what we predict. Suggested interaction of NH here, yes, with an acceptor, hydrogen bond acceptor, so the nitrogen center, aromatic nitrogen center, and forming this linear chains. No? Up, down, and up. No PP interaction. In the case of a methyl substituted, we see exactly the same. If you look to the crystal packing where in the detail, when you will see a little bit shortness of this interaction, but not more. The molecular arrangement is comparable to imidazole. So methyl group by itself has no really impact on the crystal packing. Bromine. These are all suitable interaction. NH, one again, we see here, this was a change. And additionally, the bromine has an interaction to the bromine, so bromine-bromine interaction. And we have no interaction, we see no interaction between bromine and a typical halogen bond acceptor like nitrogen. Only bromine-bromine interaction, not more. No? And this bromine has interaction to both bromine. No? This is comparable for iodobenzene, bromobenzene, something like this. No? Or you've seen the iodo-nitrobenzenes and iodo-cyanobenzenes. Very often with this zigzag of halogen-halogen contacts. What's going on with the last compound, this hydrated compound? This is really amazing. You see here all this gray shadowed interaction do not exist. So we have no interaction between neighboring molecules of this compound. If you look in detail to the crystal packing, you see neighboring molecules are linked by water. Here water, 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 water. So water, the solvent, is the dominating force, the dominating unit for molecular arrangement. All molecules are linked by water. And the only thing what you see is, talking about intermolecular interactions, you see different hydrogen bonds with water. And this is extremely, we see it very often if we're talking about crystal structure design. If water is present, water dominates the crystal packing. Yeah, very important. No? Always very nicely interaction NHN, bromine, we saw, and the derivatives do not exist if water is present in this class of compound. Okay? Well, I would say this is a short introduction in halogen bonds. See you.